Okay, maybe we can get started. Welcome to my class, everyone. Today I will give a guest lecture on the principles of deep rapid learning. The title of my guest lecture is White Box Transformers for Rapid Learning while Sparse Speed Reduction. Well, in this lecture, we have three sections. In the first section, I will mainly introduce the rapid learning while coding rate reduction. And the second section, we will learn how to construct a white box transformer crate based on optimizing the coding rate reduction objective. Well, the third part is we will consider some variants of debug architectures by design. In the last lecture, Professor Ma has used the problem of classification, right? The self-supervised learning problems to provide a rigorous characterization for the some main architectural characteristics of popular deep networks like the ResNet and also like the convolution neural network. Well, in lecture 7, last lecture, each layer of such considered such networks like the CNN and also ResNet can be viewed as to implement a gradient descent algorithm which increase the rate reduction of the objective function. And this perspective leads to somewhat surprising fact, right? The parameters and operators of layers of such networks can be computed in a purely forward fashion. But despite we use these principles, right, to construct like a redo net, but there's still some limitations. We noted that in the last lecture, all the problem we consider is a supervised learning problem. But now, especially in generative AI, most of the tasks we met is unsupervised learning. So, in this lecture, we will mainly consider how to use the coding rate reduction, this objective, right, to construct a architecture, a deep neural network architecture to handle like the unsupervised learning these tasks. So before we go forward, we can first briefly review the state of art, right? The architecture transformers. Actually, transformer is modern, the deep learning workhorse. It's really, really widely used. I think most of us have saw this figure many times. The standard transformer architecture. It consists of like the encoder and the decoder, and it has lots of blocks you can see here, like the input, the embedding, token embedding, and also position encoding. After position encoding, we have some multi-hat attention and also layer normalization, and also consists of feed-forward neural network, right? Okay, and this transformer architecture, standard architecture, is proposed by a paper, numerous paper, about 80 years ago, 2017. And this paper, over the past 80 years, has been cited over 200,000 times, right? 接近20万次, right? Really, really incredible. Just 8 years has 200,000 citations. Well, and the transformer also is a universal backbone for lots of different generative AI tasks. You can see, just take a look at the first column here. Like transformer can be used in natural language processing, the language tasks. You can see here, like a BERT task and also GPT tasks. And also transformer can be used for vision tasks. You can see here, the first line is what? The second row, the second column and the first row is vision transformer. It's based on either a transformer, new variant of transformer for vision tasks, and also other like the Dino, right? And the third column here is transformer for video tasks. You can see here, the first one is diffusion transformer. And also like the Sora, recently the Sora has been updated, right? The Sora 2, the version 2 is posted by the OpenAI team, the team, and it can generate more realistic and physically consistent videos compared to the Sora 1. Well, although transformers has achieved the empirical success, especially in applications on different tasks, but in general, when we use transformers, we always view it as black box models, just to use it and train it. And we don't know what happens at the inside layers, right? At the different blocks of transformer, we don't know how transformer transform these input tokens to output. We don't know what happens at this inside layers. That is, transformer in general are empirically designed and is a black box model. And in general, when we use transformer, the first thing we need to do is data processing, right? And we need to transfer like some real world data to first transfer it to some tokens and then do token embedding, right? The model data format we use in transformer is a sequence of tokens. Like we have some image patches or have some like the sentences, right? And we first to do is to tokenize this sentence of images. Like in like in this vision task, we first patch the vision task. We patchify this image to partition it to the different the image patches, right? And then do the rasterization, and to get a lot of different small pieces, and then flatten it, get some the embedding of this image patches. Like also like in some a language task, we have some sentence, right? We first do the tokenization and divided this sentence into different partition into different the votes. Also, in some other, we may have different tokenization approach. Maybe in some other the approaches, we decompose this sentence into different characters, not just the votes. And here we consider we tokenize into different votes. Okay, and then do the token embedding, get vectors, get a lot of vectors. So that is in transformers, each input samples is typically converted into a sequence of tokens. Actually, what is token? Token is a basic unit of information derived from the raw input. In nature, in this language task, token are typically what? Some words or sub-words, right? Also, like in computer vision, in vision tasks, these tokens are different patches. And the token embedding is a continuous formally. Token embedding is a continuous vector representation of this different token, right? Of those different tokens servers at the input in the transformers. It maps each token to a point in the high dimension space, enabling the model to process this symbolic inputs using the numerical computation. And also, a token representation is a vector that encodes this semantic and structural information of a token, typically introduced by the intermediate or the intermediate layers of transformer. Okay, and here that is this figure. We use this figure to demonstrate the whole pipeline of how transform the input to get some token representation. That is representation learning using the transformers. You can see here, like we consider a capital L layer transformer. The input is the X, right? This input data that is has a dimension is D, and the dimension is D, and we have n colors, right? We have n vectors as one axiom. We input in the transformers, and after the transform blocks, block one, like block two, and until block L, we get representations, future representations of those input, right? That is denoted by the matrix capital Z, and the capital Z has the n colors, right? Z1 until Zn. And here, for simplicity, we also denote the dimension of the representation by D, the same dimension as the input dimension. Okay. Then a nature question that is how to measure the goodness of representations, right? Learned by transformer at each layer. Well, that is, I think in last lecture, Professor Ma have introduced this concept that is, we always want to learn what representation that is compact and structured representation. And actually, of course, in the last lecture, we learned that is this compact structured representation for supervised learning tasks. But here, actually, for the unsupervised learning, that is the learning this task, we also want to learn a compact and structured representation. That is a desired property for the learned representation Z learned by transformers. And specifically, we have the learned representation have the following three properties. The first one is compressed. That is, it preserves the intrinsic low dimensionality of the data input X. And the second is linearized. That is, the learned representation Z has piecewise linear geometry, piecewise linear geometry. Okay. And the third property is sparsity. That is, these distinct modes are mapped geometrically incoherent, perfectly axis aligned. Okay, like demonstrated in this figure, we have some input, right? This input may be very complicated, highly nonlinear, lies on some unions of high dimensional manifolds, the structure. But after the transformation by the transformers, the output, the learned representation have what structure? It's like a piecewise linear, right? The structure is very structured, and also the very sparse, the future representations, like in this figure. That is the input, and this is the output representation. That is the input data, the structures. Okay. Any questions for these three properties? I think in the lecture 7, we met the similar property, right? Professor Ma raised about it. Well, for the representations learned empirically by the standard transformers, we do some visualization and empirical study. You can see here, we found that actually the learned representations by the standard transformers appear highly structured and compact. For example, you can see the first figure here. We take a look at the features, the representations. They are the same thing. They learned by the vision transformer. We do some of the visualization here, right? It's very compressed. You can see like these different colors denote different semantics of the images. You can see like this red color denote the head, right? It's very compressed. When we do the two-dimensional the visualization, project originally this data representation, right? This data representation lies in a very high dimension space, but we can use tools like the TSNE or some other dimension reduction tool to project this high dimensional representation into two-dimensional space and do the visualization here, right? Then you can see these representations are really compressed. And also we do some on other tasks, like in language tasks, we found the learned representation by transformers in language models. The first we observe is very linearized. You can see here, the second column here, and also we also found it has good property, that's sparsity, the sparse property. Actually, this is the second figure, and the third figure corresponds to some very famous hypothesis in large language models. The second figure here corresponds to the hypothesis, that's the linear hypothesis. That means the learned representation by the large language models, it's corresponds to different the learned representations, right, by the transformer in language model tasks, corresponds to different the semantics, the linear, the direction. And the third property corresponds, the third figure here, this property, sparse property, corresponds to a really famous hypothesis, that is the superposition hypothesis in language models. If you are interested, you can take a look at these two papers in the last 2 years. Of course, these are just some empirically observed properties. Okay. And the next one, we will introduce the measure, right? Introduce a metric to measure the compactness for future repetitions. I think you guys are very familiar with it now, right? In the last lecture, we have learned it. That is, the main idea is what? For the repetitions, its structure may be not ideal as we think, right? We can model here, we can model it, we can assume it, the long repetition, like a draw from a Gaussian distribution, right? Like the mean zero and the covariance is sigma, this matrix. And then under this idea, the assumption, we can use the rate reduction, this measurement, to this metric to measure the loss coding rate of it, right? We can see here the next lecture, the next slide. You can see here that is from the Professor Ma the paper in 2007. That is the average number of bytes needed to encode this long representation z up to a pure sample precision. And here small z denotes some column of the capital Z, right? Z minus Z hat is the altitude bounded by epsilon, right? Is bounded by approximation of the coding rate distortion. That is this formula one, right? That is R the epsilon is equal to 1/2 times loop determined of the inside of this matrix, identity plus d over epsilon square and times zz transpose over n, right? And actually, if the mean of this matrix is like 0, z is 0, and zz transpose over n is like the empirical covariance, right? Okay, and to sum up this, coding rate is an intrinsic measure for the volume of all features. Okay. Well, now we take a look at why this coding rate is a good metric for real world token distributions, right? Actually, there are some the main reason is because the real world data distribution, right, are typically a mixture of multiple nonlinear low dimension modes and maybe like some clusters or some manifolds. You can see here, like we do some do some visualization for the real world data, like for CIFAR 10, right? We can found it. We found it. The different class of these images lies on different low dimension manifolds. You can see like the dog images, right? Lies on the M1, this low dimension manifolds. And also for some images, you can see here, the different images, that part lies on the different objects, right? In these images lies on the different the clusters. Okay, and then a question is how to measure this the compactness of these samples, right? From this real world this data distribution. Okay. And here, right? The metric we introduced here is to measure the compactness of the Gaussian distribution for the long representation. But actually, the real-world data is typically like a mixture of the multitude of low-dimensional modes. It's not as ideal as we think, right? Like a Gaussian distribution is maybe a very complicated mixture of some distributions, maybe like lies on a union of low dimension manifolds, and this manifolds does not satisfy the Gaussian assumption. So the question is how to measure the compactness of these samples from the real world complicated distribution. And that is we can first do the the transformation, right? Use the transformer to do the transformation, and then measure the representations learned by transformer. That is, although we cannot directly use the coding rate to measure the original the data distribution, but we can use it to measure the learned representations by transformers. You can see here the learned objective, right? The desired, we have the desired distribution of tokens. That is the learned distributions of tokens by transformers. We have it to be like a mixture of Gaussians or low dimension Gaussians. You can see here we have some image patches, right? And then after the transformation layer by layer, transformation by the transformations layer by layer transformation, right? Then we get the learned representations. That is the output of the intermediate layers of transformers satisfy this good assumption. That is a mixture of low dimensional Gaussians. And specifically, this mixture of low dimensional Gaussians, that is, we model the learned representation satisfy the following the data assumption. You can see here, given orthogonal basis UK, we assume we have K mixtures UK, and this notion denotes it's a collection of K, capital K, the orthonormal matrices, and each one the dimension is D times P, and we have K of them, and then we desire each feature ZI. This ZI actually is some column, ice column of this capital matrix Z, have the marginal distribution given as follows. That is, this ZI is the U SI and times alpha, and this SI is what is actually is the label of this ZI, right? You can see SI, that is like a membership of this is membership of the ice samples, and here we set it to be the random variables corresponding to the subspace indices, and the RFI is like the some coefficients, right? Since this ZI equals to, you can see here, like we consider the SI to be some we can write it. Suppose that like this I, like this I, right? This sample I, ZI, like the index belongs to some K's cluster, right? The K, small K, okay? And this K is index of this, right? And this notion, this one, this capital, this like bracket K, this denotes 1 to capital K, this index set 1, 2 until K. And suppose this I belongs to this cluster, right? And then that means this ZI, this features is like UK, okay, right? Belongs to this UK denotes the orthonormal basis of K's cluster, and times the coefficients, right? The alpha I, right? And here, alpha I, we have assumption as alpha I. Alpha I is like what? Like a latent vector, right? In this subspace, we assume it to be the standard normal Gaussian distribution, right? Here we assume the dimension of UK to be what? D times P, right? In general, P is much smaller than D. Right? That is the latent dimension of this data, of this orthonormal basis, right? The latent dimension P is much smaller than the ambient dimension D. And then what is dimension of this alpha I? The coefficients is must be P, right? The latent dimension. Okay, that is this model means a mixture of low-rank Gaussians. So what is distribution of this sample ZI? If this UK is given, you can directly compute it, right? Use this assumption alpha I. That is, this AI is actually this alpha I is a full dimension Gaussian, right? Because it's the identity, the covariance matrix is the identity. But this features here under this assumption is a degenerate Gaussian. Degenerate is a Gaussian random variable. you can verify the mean is 0, right? Use the definitions, you can further compute it. The covariance of this is UK transpose. Use definition of covariance, right? That is to compute like expectation, ZI transpose is to compute the covariance, right? You can verify the futures ZI, is a degenerate Gaussian random vector is mean 0, and the covariance is UK transpose. And alpha hat here, right? Because we assume it to be a full dimension, the Gaussian is latent space, the mean 0 and the covariance is identity. But this identity is P, the dimension is P times P, right? Okay. Any questions for this assumption? Sorry. So in this sense, we also understand why the real-world distribution sometimes is not easy to learn, right? Because it's a degenerate distribution. The covariance here is not a full rank, as we know, right? In most of the case, the degenerate assumption is not easy to learn. Okay, so here we can use the coding rate to measure the distributions, to measure the loss coding rate of the lambda distribution when it satisfies the mixture of low dimensional Gaussians, this assumption, right? You can see here that is the coding rate with respect to this model, right? The mixture of low rank Gaussians, that model can be computed as follows. This is for the compression part. As we learned in the last class, right? We can first recap a little bit about the coding rate for the supervised learning problem. For the coding rate for the supervised learning problem, right? It has like delta R has two terms, R minus RC, right? In general, we have the assumption, we have the information about this assignment pi, this matrix, right? The assignment, this one, we have information about it. And then we can define this RC term, this form. We can first look at it a little bit. That is like this form, right? The RC, this one. For supervised learning, okay. This is a trace pi k, right? And this 2n and log determined identity plus, right, the d over epsilon. And this one. However, for the unsupervised learning, right, for unsupervised task, we do not have the information. We do not have the information about this assignment. We don't know the futures we learned belongs to which class. We don't know. So how to encode, how to represent this coding rate, express this coding rate. Actually, the approach we use here is do a subspace projection. We project the futures. Yeah, we need to understand the geometric interpretation here. That is, we project the futures, right, V, to each subspace. As we learned in linear algebra, if UK is like a orthonormal matrix, right? Like D times P, right? The orthonormal P is much smaller than D. Then UK transpose is what? is like a projection onto a linear subspace spanned by this matrix U, right? Like this is a submatrix. This is a subspace. Like span, the span is UK, right? Okay, and what is this operation means here? That is project each color of this matrix Z onto this subspace. That is geometric interpretation here. So then we can further use the coding rate, right? This definition here to measure the distortion of these projected features onto this subspace, right? For each subspace K, right? Because we have small k equals to 1 to until capital K, we can project the coding rate onto each subspace. You can see here, right? That is UK transpose times UK transpose. And you may be curious here, it is UK transpose, right? But why we just have UK transpose, not UK transpose, right? Because we use orthogonality here. We can take a close look. Recap the definition of the coding rate, right? Is RZ epsilon, right? This is coding rate for the features in the full dimension space. Okay, in the full dimension space, after we do the subspace projection onto the K subspace, right? The obtained features is like this. Then plugs in, right? UK, if we plug in the UK transpose, doesn't work. Plug in the projected features onto case subspace into the definition. All right? The dimension should be node D, right? Because out of the projection, the dimension into restricted to this subspace should be P. Okay. And you can observe here, right? This is like this, but use a property that is log determined I plus alpha ZZ transpose equals to what? Equals to log determined I plus alpha ZZ transpose, right? Z transpose Z, right? Use this property. The property of log determined, right? Then you can use this property and the above equals to, right? Use this property, okay. Use this property here. And you can further compute, that is UK transpose Z transpose, right? UK transpose Z, right? And then what happens? That is Z transpose UK transpose UK, right? UK transpose Z. And this is what? This is identity matrix. That is why we can go from the coding rate for whole dimension space, but full dimension space to the subspace dimension space, but the term here is UK transpose Z, not the UK transpose Z. Okay, we use the property of log determined, right? The Z inside the Z transpose can be replaced by the Z transpose Z, right? Keep the value, doesn't change. And then we go from there to here. Okay. Any questions for this calculation? Okay, if not, we go ahead. You can see here, this is an interpretation for each term in this formula. That is, UK transpose means we project the features these right onto each subspace UK, and the R this term actually that is this here is to measure coding rate in each subspace. It's like the interpretation here, right? We have some data points on the full dimensional space, and we first projected onto this low dimensional space spanned by UK, and the measure is coding rate. Well, and then we can further use the following objective function to measure the information gain. That is the difference between the coding rate of the whole and the coding rate of the parts, right? That is known as a coding rate reduction. You can see here, this first term is like the expansion term. And we have learned in the last lecture, the Professor may spend lots of time to explain this concept. And the second term is like the compression term, right? It's to measure how compressed the parts, right, are contractive. And first term is the expansion term. It's like to measure how expanded all features are positive if we maximize this objective function. Any questions for this objective function? Well, and note that a key difference, when we can take a look at the next slide here. This one. You can see here, compared to the standard, right, for the maximal coding rate reduction, there's an objective function for supervised learning. In the supervised learning setting, we have the pi_k, right? As I just mentioned, the pi_k, this information, that is the assignment of data points onto the case cluster. And then that part, the RC, that part is defined based on this pi_k. Pi_k is given, it encodes it encodes the membership of sample in case class. And the inside in the pi_k, right, there is d over epsilon, but you're compared with the objective function of the coding rate here, right? For when the data points have lies on a union of low dimensional Gaussians, or supervised learning tasks, right? We do not have the assignment information. We do not have pi, but like here, this UK transpose is like to implicitly given a membership. Why I see this? We can do some calculation. You can get some geometric understanding for this projection. That is another interpretation for the objective function, this coding rate. This objective function is like to give an implicit membership as the role of pi_k. Okay, like suppose we consider like in the mixture of low-rank Gaussians, right? We assume that like Zi, right, belongs to the case class. Okay. I can write in this one. Like the I data point belong to case cluster. That means this Zi, right, equals to UK times AI, and AI is the coefficients. So if we do the projection of these data points onto case subspace, and this subspace is spanned by this UK, right? And that is UK transpose Zi, right? This computation here, UK transpose, we just take the ice color equals to what? It's UK transpose UKAI, right? It's equals to AI. Get the latent coefficients. Of course, here we assume the other subspace L not equals to K, UL transpose UK equals to like almost to be orthogonal. Okay. And then we do the calculation that is UL transpose VI. Right? What happens? It's almost zero because the orthogonality between different subspace, right? So this norm significantly is larger than one, larger than zero. And this norm, right, the norm of this projection is close to zero. So after this projection onto a data point on the different subspace, you can easily to identify this features Zi belongs to which subspace, right? If Zi is sampled by the mixture of Laurent Gaussians, that is why I say this projection, that one, the operation there is like do implicit assignment as a role of the pi k in the coding rate for the supervised learning task, right? This orthogonal projections effectively serve as implicit membership labels, identify the subspace to which this token representation belong. Because of this interpretation here, right? The Zi satisfies this assumption and this subspace, different subspace, like close to orthogonal to each other. Okay, any questions? Geometrical interpretation for this part, right? For this RC resistance, the compression term. Okay. And here, so maximize this objective function, the maximum coding rate reduction, this, right? If we maximize this coding rate reduction objective, the first part is to, as we said, measure how expanded all features are contrastive, right? And the second term, RC resistance, is to measure how compressed each parts are contractive. And like as illustrated in this figure, the objective function is to promote statistical independence or geometrical incoherence, right, of different parts. And here is the comparison of the objective function to MCR for supervised learning. Just to recap a little bit for what we have learned in the last class, the objective function here, and right, is also like a RZ minus RC term. And in that class, we learned how we can unroll the grid descent for optimize this objective function and to induce a redo net, right? It's similar to the rest net. That is what we have learned in the last class. And here, I want to mention, without Professor Ma may forget to mention in the last lecture, you can see here, that is, our recent study has shown that the MCR, this objective function, right, with regularization, L2 Fresnel's norm regularization there, with this regularization, the objective function has very benign loss landscape. Specifically, what does it mean? That means this objective function, though we consider the optimization variable is Z here, is features. That is, every critical point of this problem that is gradient to be zero is either a local maximizer of this problem or a strict saddle of this problem. We have learned this too, right? In the lecture 4, I believe. That is also I instructed about a month ago. Is either every critical point is either a local maximizer or strict saddle point. And each local maximizer corresponds to a future representation that consists of a family of orthogonal subspaces. And what does this mean? That means if we use grid descent, right, with random initialization, well, we always convert to. If we use grid descent with random initialization, recall the result we have learned in lecture for the optimization that lectures. If is either every clear point is either a local maximizer or strict set point. In that lecture, we learned grid descent with random initialization almost always escape from strict set point, right? Most always escape from escape strict set point. Then grid descent, this first order algorithms convert to must convert to local maximizers. So in this sense, the objective function for this MCR for supervised learning problem, right? The MCR objective function for supervised learning problem has a benign loss landscape. That is why in practice, like we use this objective function for supervised learning tasks, we can always convert some good point, achieve very high like classification accuracy. Because we can theoretically justify it can convert some good local maximizer. And this result is published in our last year, the ISML paper. Is a theoretical paper. The title is Global Geometric Analysis of Maximal Coding Rate Reduction. We do a complete theoretical analysis for the objective function of MCR for this supervised learning task. And also we do a very simple visualization here. You can see we show what? We show this is a loss landscape two-dimensional visualization for the objective function here. It consists of like local maximizer and a global maximizer. Of course, global maximizer is also a local maximizer, right? And also other point like the strict saddle and local minimizer. Here, the strict saddle, this definition is broad definition. It also includes the local minimizer. Yeah, it's broad definition. It's not the narrow, like must be a set point. Okay, just you have a negative descent direction, we can say it's a strict saddle point. Okay, and then if we run grid descent, we always convert to like this point and this point. We will escape like this point and this point. Okay, any questions for this result? Okay, if not, we go ahead. Then we go further. And in the previous slides, right, we considered use the coding rate to measure the futures, the coding rate of futures when it satisfies the mixture of Gaussian, right? This assumption. And then we can further introduce a sparse rate reduction, this objective function, because note that the reduction, the objective function, is invariant to arbitrary joint rotation because of what property is this property, right? That is log determined. You can verify this. That's log determined I plus alpha ZZ transpose, always to log equal to log determined, right? Z transpose Z. And if we replace this Z with times like orthogonal transformation before Z, right? U is like the D-dimensional. The orthogonal matrix, it won't change the objective. That is what we say the reduction objective function is invariant to arbitrary joint rotation of the representations as subspace. So optimizing this rate reduction may not naturally lead to axis aligned, right? That may not naturally lead to the sparse Z representation. You can consider here, if we optimize, right, from the reduction, like in this originally like this form, after the optimization, it may like this form, right? It's not sparse. Suppose this is standard XY axis. It's not aligned with the XY, this axis, right? So, but we would like transform this representation to be more compact, right? More compact and structured representations. That is like the third figure that shows here. that is this lambda rotation aligns with the x and y axis, right? It's very sparse. So how we can achieve it? Actually, we do a very conceptual, right? A intuitive approach is to do what? It's to add a sparse regulator to the objective function. Because this is a maximization problem, right? We do the add a minus lambda times the zero norm of this objective function. Yeah, and then combine this one, this regulator with the reduction objective function together. We have this one, right? The RZ minus the lambda times zero norm. And this is Z, is a features learned by some neural network. And what we want to optimize is this theta, the network parameters. Okay. And the total, the intuition is here. First, we use like the loss part, right? The RC minus R minus RC, that part, right? To make this two subspace like more incoherent. And after the transformation by the regularizer, the zero norm, we can further transform it to be the axis aligned representation, is to be more sparse. Okay, and then, but as we know in optimization, right, the L0 norm is not a good regularizer. In most cases, in the first case, is NP hard, right, to compute it. So here, to improve the computational trackability, and also we relax the L0 norm to be the L1 norm. Sorry, this is a typo here. It should be trackability. It's not the traceability. Okay, we replace the L0 norm, right? The L0 norm to be the L1 norm, with this one. And then we combine this L1 norm with the expansion term, right? And then we get a specification. We call these two things together is the specification term, and this part is to be the compression term, right? And that is what we consider the sparse weight, the objective function in this lecture. This is more the effective objective function to optimize. You can see here, right? The whole figure for this. That is, we have some high dimensional data, and after this, the transformation, right? The long representation, this representation will optimize this objective function. The long representation is compact and structured. Actually, the approach here and the spirit here is same as we have learned in the last lecture, but we apply this objective function, these principles, maximum coding rate reduction, these principles to unsupervised learning problem, right? Under the assumption what? The learned features is like a mixture of low dimensional, it's like a mixture of low dimensional Gaussians, right? And then we can induce objective function and consider it to be sparse. Okay. Any questions? Okay, if not, we further consider use this neural network, right? What we have learned there to construct, use the learned objective function, sparse weight reduction to construct the neural network. Like we have learned in previous lecture, we can use the ISTA, this algorithm, right? The proximal gradient descent, this algorithm to induce a LISTA, this neural network, right? From the ISTA to LISTA. I think we have heard this concept many, many times in this lecture, in this class, right? That is how to induce a neural network, construct a neural network from some algorithms, optimize the some objective. Like in last lecture, we construct the ReduNet by optimizing what? The gradient descent for optimizing the maximum coding rate, this objective function, right? For supervised learning. We construct ReduNet layer by layer. Each layer corresponds to a gradient descent step. Actually, it's gradient ascent. Okay, it's maximization, right? gradient ascend the step, and then we construct the redo net, this neural network, and each layer of redo net corresponds to a gradient ascend step, right? And use the same approach, we can further construct a white box transformer architecture by optimizing the objective function of sparse reduction. And here, I give a very clear definition, according to my understanding, for the white box transformer and also white box neural networks. And Professor Ma always mention, right? White box, white box. What is white box? Actually, in this class and also in our book, the white box deep neural network means layers of network can be interpreted as an unrolled optimization scheme to iteratively optimize some goodness of the learner representations. That is what he always mentions, the white box, something, right? That it means the architecture of this, like some layer, right? Some layer, like else layer, this architecture corresponds to some optimization updates. Optimization, right? Optimize some loss here. That is the architecture design of this neural network. Corresponds to the gradient, corresponds to some optimization algorithm step. That is what he means, the white box. Any questions? Actually, this is the most important concept in our book and also in this course. The main concept, white box, deep networks, especially these two lectures, right? Last lecture, the white box, the redo net, and this lecture, we talk about the white box transformers. Okay, if not, we go ahead. Then we use the lecture, the concept, right, to further construct the architecture that is transformer architecture from optimizing the sparse rate reduction. That is, we incrementally optimize the objective function, and then based on the objective, the algorithm update, we can construct the neural network, the architecture. However, we note that if we directly apply the gradient descent to optimize this objective, what happens? Or proximal gradient descent. The algorithm update may be very complicated because RD and RC term here, log determined, take the gradient of log determined what we will have, what we will map, the matrix inverse, right? So here, we go back here. You can see in this, right? In this concept, right, we do not repel. We must use gradient descent. We don't repel. We just say it can be some unrolled optimization scheme. It may be gradient descent or some other algorithms. We do not require we must use gradient descent, right? So here, we take a different approach to construct neural network. That is, we use the alternative minimization. We first take a gradient step for the compression term, and then take a proximal gradient the approach for the sparsification term, and then alternatively to update it. And each step, right, each layer of the constructed neural network corresponds to these two steps. Yeah, not just directly apply gradient descent, right, and then construct neural network. It's not. Okay, and now we see the details. We take a look at the details. And here, this figure, I just briefly mentioned it, right? This figure is to if we directly use gradient descent, right? We can construct, but we take a different approach. This is what we have used in the last lecture, like to construct redo net, right? Gradient ascent, and then construct the redo net, the neural network. You can see here, that is what we said. We use alternative minimization. You can see here, like else layer corresponds to the else update, else step of some optimization algorithm. Is it? And here we decompose the else layer operator FL to be a composition of two functions, two operators. I have 2L and F1L, the composition here. And then we first implement the first step, the compression tend to be this. That is F1LZL, right? The generated updates. The generated update is the L plus 1/2, right? The intermediate step, the intermediate output, that is to be the ZL minus, that is take a gray step with respect to the compression term, right? Note that here we transform the maximization problem, right? Maximize. The objective function is originally is maximize the maximal coding rate reduction, right? And here is maximized, right? So we first transform to be the minimize, add a minus to be the whole objective function, right? So we go from there to here, minimize, you can see here, minus plus rate reduction. That is why it becomes a positive minus, right? Okay. And then we can take with this minimization objective, we can use the alternative minimization scheme. And the compression term here, you can see that is to take a gradient step for this compression term. And then for the specification term, right? For the specification step is doing what? F2, this operator is doing what? Is like do a proximal gradient descent. But actually here it's not like directly apply the proximal gradient step for this, right? If we directly apply the proximal gradient descent, here what it should be is like L plus 1 over, is like D minus what? The gradient of this, right? Gradient RDL, but here is different. We will see the details. Okay. I think we can take a break, take a small break, and come back later. Okay.